All right, looking here at one of our special right triangles, I'm not sure if everybody had a chance to really digest this too terribly much the other day when we were starting with this, but a special right triangle, 30, 60, 90 right triangle, always has a very special characteristic. And if we were to go and maybe look at our calculator and talk about, well, I know what the sine of 30 degrees is. Sine is opposite over adjacent. I think if I ask my calculator for that, I'm going to get a really interesting answer, I believe, of 1/2. So if you take your calculator and you just ask your calculator, hey, what is the sine of 30 degrees? And I'm going to take my calculator out here, and I know it's not the best thing in the world, but I'm going to go sine of 30 degrees, and it says that it's 1/2. So if I were to put that information into my triangle, sine opposite over hypotenuse, I'd have a 1 and a 2, and I'm going to get that out of the way. And most everybody, I think, if we wanted to figure out the missing side now, wanted to figure out what this side over here is, we might say, well, I could do the Pythagorean theorem. I could go 1 squared plus the missing side squared equals c squared, and I could get x squared, 4 minus 1 is 3, and I could get x equals the square root of 3, and I could actually fill that side in. And that particular triangle opposite the 30 degrees would be a side whose length is 1, and across from the 60 is a side whose length is square root of 3, and the hypotenuse, the largest piece, is 2. And the beauty of this is it doesn't matter whether I draw a triangle that is a ton bigger than this one, a lot smaller than this one, the ratio, the trig ratio, the sine of 30 degrees opposite over hypotenuse is always going to be 1/2. And so what that allows us to do is it allows us to look at triangles and say, well, if I know what that ratio is, I can set up a proportion and solve a proportion and figure out the missing sides if I know that it's a 30, 60, 90 triangle. And if I know any one of these three sides, I can always find both of the other ones. So I'm going to put in here for us another 30, 60, 90 triangle, and I'm going to identify 30 degrees up there, 90 degrees, so 60 degrees, and it doesn't really matter what side I pick, but just for making things a little bit easier right now as a warm-up, I'm going to pick and identify that this side across from the 30 degrees is 4. And if I know that, and I know that the 30, 60, 90 triangle ratio is 4, I should be able to conclude that the side across or opposite the 60-degree angle is always whatever the side opposite the 30-degree angle is, times the square root of 3. And that the side across from the 90-degree angle is always twice as much as the side across from the 30-degree angle, so 2 times 4 is 8. And I could check that with the Pythagorean theorem. I could verify, is 4 squared plus 4 square roots of 3 squared equal to 8 squared? And I could check it. I mean, I prefer not to have to do this. I would like to avoid doing this on a regular basis if I could. 4 squared is 16, square root of 3 squared is 3, so 16 plus 48 equals 64. Yes, that's true. So it appears to work. And the key is, if I can figure out any one of the three sides, then hopefully I can work around and figure out the other sides. So the 30, 60, 90 triangle doesn't have to always be oriented the way I oriented the first one. We just have to know that it's a right triangle. We have to know that we have a 30-degree angle. We have to know that we have a 60-degree angle. And then they have to tell us a side. So just for something different, I'm going to identify that the side, the hypotenuse, I'm going to let it be 14, just because I want to. And then I would be able to ask you, well, you should be able to find the side across from the 30. You should be able to find the side across from the 60. And if we look at the relationship from up above is whatever is on the hypotenuse is always twice as big as what is across from the 30. So if I think about the hypotenuse, 14, being 2 times something, well, 14 is 2 times 7, so that must mean that the side across from the 30 degree is 7. And the side opposite the 60 is always the square root of 3 times as much as the side across from the 30. So I can say 7 square roots of 3. So given a 30, 60, 90 degree triangle, given any one of the sides, I should be able to figure out the other. And these examples are rather straightforward. We can do another example. We can put a 60 degree angle up top here, 60 degrees, 90 degrees, 30 degrees. And again, as long as we know any one side, we can do our work. So in this example, I think I'll tell you that across from the 60 degree angle is 5 times the square root of 3, which might seem a little bit weird, but if I go back to the original, whatever number is across from the 60 degree angle is always the square root of 3 times as much as the side that's across from the 30 degree angle. So here I have 5 times the square root of 3, which is convenient because it's 5 times the square root of 3. So across from the 30 should be 5, and now I have the relationship of 1 and 1 times the square root of 3, or in this case 5, and 5 times the square root of 3. And the hypotenuse is always the biggest, it's always twice as much as is what's across from the 30 degree angle, so I can put in that that should be a 10. And I'm able to kind of get those visually by looking at what we have. So they do get a little trickier, and they get a little trickier when your picture doesn't quite match what you're expecting. Okay, maybe the numbers just aren't falling into place as nicely as you would want. I'm going to put 60 degrees in that corner, 30 degrees in this corner. My picture doesn't look like it's drawn to scale very well, but if it's 30, 60, 90, the relationship holds. And I think I'm just going to put some really weird number like 7 across from the 60 degree angle. Now, it's too bad that it isn't 7 square roots of 3, because if it were 7 square roots of 3, we would know across from the 30 would be a 7, and across from the 90 would be a 14, like the picture straight above here. But it's not set up perfectly, so what I would like to do is I'd like to go back and say, well, the side across from the 30 degree angle always compares to the side across from the 60 degree angle in this relationship, this ratio, that the side across from the 30 is always 1, and the side across from the 60 is always the square root of 3. That's the ratio. And in our picture, we don't know what the side across from the 30 is. I'm just going to call it C. So the side across from the 30, I don't know. The side across from the 60 is 7, and here we've set up this ratio, and if I cross multiply, 7 times 1 is 7, and the square root of 3 times C is that weird number, square root of 3 times C, and our job is to figure out what C is. So in order to do this, because it says square root of 3 times C, we're going to have to divide both sides of the equation by the square root of 3. So now we have this really strange number, 7 divided by the square root of 3 is C. And if you recall last year in algebra, you might have talked about rationalizing denominators. Anytime the denominator is a radical number, how you can multiply the numerator and the denominator by that radical number to get rid of it. So 7 times the square root of 3 is 7 times the square root of 3, just like 7 times x is 7x. And the square root of 3 times the square root of 3 is actually 3. So we get that this side across from the 30 is 7 square roots of 3, 7 square roots of 3 divided by 3. And that seems pretty messy, but that's just the way it is. But what's helpful to us is the hypotenuse is always twice that. Whatever your side is across from the 30, your hypotenuse is always twice as much. So if I want to take this number and take twice as much, it's going to be 14 square roots of 3, all divided by 3. And that's just not a problem I really care to check. I could check it with the Pythagorean theorem. I could say a squared plus b squared equals c squared, and it should work out. But ideally, the goal behind these 30, 60, 90 triangles is to get you to not have to do that. It's to get you to say, I believe in the ratio, I believe that I can set up the cross product, and I can solve. So one last trickier one. We'll set up a right triangle. This looks a little bit better, 30 degrees in the corner. There's the 90, there's the 60. And I think I'll just give us a hypotenuse amount. And why don't I give us a hypotenuse amount that's just not very work-friendly? I mean, something like 9. You know, unfortunately, 9, well, it's twice as much as something because it's in the hypotenuse spot. 9 is twice whatever, well, it's twice 4.5. So across from the 30 is half of 9. And across from the 60 is supposed to be whatever across from the 30 is times the square root of 3 from the ratio. And I can get those 30, 60, 90 triangles every time just like that without having to do the Pythagorean theorem, without needing a calculator.